Quarry Crew is a carbon offsetting tool which has been designed for the problem statement developing a software solution for quantifying the carbon footprint and identifying carbon neutrality pathways for Indian coal mines. Which you are seeing is the front page of our website where you can see a registration button and also a login button. For the new users, you have to click the registration button, which will be redirected to the registration page. If you are already a user, you can click through the login button and you can log in through your registration ID. When you click the registration button, you will be redirecting to the registration page where you can see four things: registration ID, mine name, mine type, role, location, and password. We have designed this keeping in mind about the security constraint. So first, the admin will be registering the mine in the website, and the registration IDs for particular employees of that mine will be given or assigned by the admin to that particular user. By this, we are ensuring the authenticity of the user. So I will be redirecting you and showing you how this works. So by this, the outsiders won't have the access to access the data of the website. Here, this is the Quarry Crew's homepage where you can see basic details or information. So this is carbon emissions. Just we have given the data of that particular year, and these are few sustainable methods which can be seen by the user, and these are few blogs which can be insightful. We have kept this here in the homepage. In the header section, we have included navigation elements such as home, dashboard, mine name, and user profile. Below the header section, we have four key components like explore, carbon footprint section, sink analysis, carbon neutralization. Coming to the carbon footprint section, we have designed as a calculator consisting of two primary calculators, that is emission calculation based on activity and carbon per capita emission. Here, the carbon per capita emission calculator calculates factors in the number of workers and their working hours to determine the carbon emissions. For instance, let us take 485 workers and 48 hours. When we calculate, the system will compute the total carbon emission generated because of 485 workers in the duration of 48 hours. Let us walk through the emission calculator based on activity. Here, for each activity, we have taken different factors. For example, let us go through diesel usage. Here, as you can see, amount of diesel used is the factor which has been used here. Let us take 487. And as you can see, this is the carbon emitted due to 487 liters of diesel, and this is the contribution of diesel used in the total emissions. We have designed the emission calculations in such a way that the result can be reused throughout the website for prediction and visualization purposes in subsequent sections. This approach minimizes redundant inputs and enhances user experience, making the process more efficient for both users and to sink analysis section. In this section, we have integrated a map displaying two key elements for carbon absorption. The green points represent afforested lands and blue points represent the wetlands. So these two categories, afforested lands and wetlands, serve as the major components of carbon absorption in this analysis. On the right side of this section, we have displayed three key metrics. Current carbon sink capacity. This shows the mine's current capacity for carbon absorption, indicating how much carbon is absorbed per year in the surrounding areas. Required carbon sink capacity. This metric displays the additional capacity needed to absorb the remaining carbon, highlighting any shortfall. Sink gap. This represents the difference between the current and required capacity, indicating how much needs to be enhanced to bridge the gap. The result from the sink analysis are directly utilized in the carbon neutralization pathway section, where we will be discussing how these insights are connected for developing strategies for improving carbon absorption and achieving neutrality. Walk through carbon neutralization pathways. In this section, we have developed four key strategies achieving carbon neutrality. Those are renewable resource shift, afforestation metrics, electric vehicle replacement, and methane conversions. Let's start with renewable resource shift. We have taken three factors into consideration for each mine. 1. Solar irradiation value, wind speed value, nearby reservoir value. Solar irradiation value is for suggesting solar power plants, this is for suggesting windmill plants, and this is suggesting hydroelectric power plant. So these values are used by the model to calculate a score, and based on the score, we recommend two options: best fit and second best energy source for that mine. For example, in some cases, we may suggest solar and hydropower plants. Additionally, for each suggestion, we have provided two important metrics: investment, how much needs to be invested to build that plant; carbon reduction potential, the estimated amount of carbon reduction that would result from that shift. For solar plants, the area required for installation is considered, while for hydroelectric power plants, the proximity nearby reservoir is factored in. Based on these inputs, our model calculates the most suitable energy shift for that mine. Let us go through afforestation metrics. See electric vehicle replacement section. In this section, we have visualized the shift to electric vehicles from the mine's operations. The aim is to show how transitioning from conventional vehicles to EVs will impact carbon emission reduction. We have focused on three key factors: total EV vehicles, investment, and impact. Number of EVs to be considered is here taken in the total EV vehicle section, and how much needs to be invested to replace these vehicles is given in here, and the estimated reduction in the carbon emissions after shifting to EVs is given in this section card. Below these factors, we have two additional components. Those are activity-based shift graph which is this one. This visualizes the current vehicle emissions compared to the emissions after the shift to EVs. It provides a future projection of how emissions will change post-EV transition. And coming to the next one, it is carbon reduction by activity. This shows the carbon reduction resulting from replacing vehicles with EVs for specific activities. Below these things, we have given a table which shows activities and current number of vehicles used for each activity, the number of EVs to be replaced for each activity, the corresponding carbon reduction after EV replacement, and the investment required for the replacement. This allows users to clearly see the cost involved and the reduction in the emissions for each activity. We talked next is the afforestation metrics. This section uses data from the earlier sink analysis and includes three factors, which are air quality index, which is calculated using total emissions data from previous section, available area, that is the land suitable for afforestation based on state afforestation policies, and the next is population, which is around the mine location. And next is, using these factors, we suggest how many trees should be planted in the mine area and the type of trees that are suitable for that region. The air quality index is calculated using an emission-based formula, and the available area includes unused and convertible lands that are identified. Additionally, we have integrated a map that visually shows the afforestation area. By entering a specific radius, the map zooms into that location and all related metrics update accordingly. After completing the afforestation as suggested, the website calculates and displays how much the sink gap will be reduced, helping the users understand the impact of their efforts on carbon absorption. Part of the carbon utilization pathways, we focus on converting methane emissions. That is, how the emitted methane is turning into useful resources for energy generation and other applications within the mine. So in this section, we have structured this into several components. First, this is total methane emissions. This card displays the total amount of methane emitted by the mine. This is methane to energy conversion. This card shows how much of that methane is being successfully converted into useful energy. Below this, we have represented few graphical representations. So first one is methane to energy and CO2. This graph shows the percentage of methane used in different sectors like electricity generation, heat production, and CO2 capture. And the next thing, methane capturing system. That is, this graph shows details how much methane is being captured through various methods such as underground storage, ocean storage, and geological storage. And the next one is methane capture breakdown. Here we illustrated the breakdown of methane usage, whether it is stored, utilized, or released with the preventive measures to minimize emissions. And finally, below these things, we have kept two things. One is CO2 savings. This section displays a graph showing how much CO2 is being saved or reduced as a result of methane conservation efforts or methane emission reductions throughout the years. And here this is energy usage according to activities from methane. This graph or this cards show how the captured methane is utilized across different activities in the mine. On to the final section, that is the dashboard, which is the central and most important visualization sector of our website, offering a comprehensive and user-friendly overview of all the aspects related to carbon emission and management in the mine. It is integrated with all the crucial data points, presenting them in an intuitive way by also addressing the entire problem statement efficiently. We have designed several key sections and graphs on this dashboard. First one is credit trend. This section displays the total number of credits that the mine holds and how they are being managed or traded throughout the year. Users can track trends in the credit earned over time and understand how efficiently credits are being utilized. Coming to the next one, which is credit distribution pie chart. This pie chart breaks down how carbon credits were accredited from various projects or activities, showing how these activities have contributed to the total credits. Next one is sink gap analysis. This graph provides a period by period view of the sink gap, showing how much carbon absorption capacity is still lacking and how efficiently the gap is being addressed. And the remaining things are carbon neutralization pathways progress bar. That is, each pathway such as renewable energy shift, afforestation, and etc. is represented by progress bar. This bar tracks the progress towards set targets over the years and how much has been accomplished so far. And the next one is emission trends. This graph shows the carbon emissions trend over different periods, either by month or by year. Users can select a specific period and the dashboard will dynamically update to reflect the emissions data for that chosen time frame. And the final thing is activity-based emissions. This section lists all the activities that contribute to emissions in the mine. It provides detailed breakdown of emissions for each activity, allowing users to understand which activities are the biggest contributors. The dashboard's unique feature or our website's USP is its ability to calculate everything based on a single user input, which is only given in the total emissions calculator, and this is helping to reduce the redundancy and making the data easy to access and analyze. So this is our Query Crew website, which has been developed for the problem statement 1644. Thank you.